Hi everyone. I want to talk to you today a little bit about why things sink or float when you put them into a fluid like water, or a balloon floating or sinking in air, which is another fluid. When something is sinking or floating, you have to think about the term buoyancy, and you also have to think about density. We're going to talk about all of those in this quick video. So I want you to see this picture on the left. It's a picture of a block of wood, which typically most types of wood are less dense than water. It's floating, and you can see that the water level has risen because some of the volume of the wooden block has pushed some water out of the way. We call that water displacement. So the water has been displaced. As a result, it has to climb up around the sides of the block, and as a result, the block floats. So if I asked you what causes objects to sink or float in a fluid, most people who have at least a basic understanding of science would probably use the word density. They'd say things that are more dense than water will sink, things that are less dense than water will float. But we probably know it's a little bit more complicated than that, and so we are going to break down a little bit what density has to do with buoyancy. So here's two different blocks of wood. One is pine, one is oak, two different types of wood which are both less dense than water, but one is a little less dense than the other one. So which one is less dense? We can probably guess that the pine is less dense because it's floating a little bit more. The oak is a little bit denser, so it's closer to the point of sinking. The difference between these two is density, but again, it's a little more complicated than just saying the word density and that's the end of it. So I'm going to bring back something that we've already learned, which relates to pressure. Pressure is greater in a fluid when you go to greater depths. The farther down you are in a fluid, the greater pressure you feel. How do we know that? Because we have a relationship that we've already talked about that says that the pressure a fluid exerts on a surface is equal to the density of that fluid multiplied by the acceleration due to gravity multiplied by the depth in the fluid that you are. So that relationship says right there that there's a link between depth and pressure. So greater depths, greater pressure. You can see that with the white pressure arrows that I've added into that diagram by the oak block. So since there's more pressure on the bottom than there is on the top, since the bottom of the object feels more pressure than the top of the object does, there's going to be a net force directed upwards. We call this net force, in this case, as a result of a fluid, the buoyant force, or force of flotation, or force of buoyancy. You'll hear it in multiple different ways. I'll usually just call it the buoyant force, and it's symbolized with an F and a subscript B. So let's talk about this buoyant force and what it has to do with things floating or sinking. Here's a conceptual example where I'm going to drop a block of wood into some water and we'll see what happens. So here's our setup. A wooden block is dropped into a container of water. How will the block behave as a result of all of the forces acting on it? So let's think about forces, because that's a really good place to start when you're analyzing a situation with physics. That block of wood right there is currently in the air. It hasn't yet reached the water. So there's only really one force significantly acting on it, which is gravity. So I'm going to throw out a number here and say that the force of gravity acting on this wooden block is 200 newtons of gravity. So that's the force pulling it down. Now, are there any other forces acting on that block at this moment? Not significantly. You could argue perhaps that the air has a little bit of buoyancy acting on the block, but it's so insignificantly small because of the thinness of air that I'm not even going to bother putting it into this diagram. It's insignificantly small. So since gravity is the only significant force acting on it, there's nothing to cancel gravity out, and so the box is going to accelerate. So it's going to accelerate towards the water, it'll splash, and let's go forward in time to see how that box is going to behave now that it's in the water a little bit. So we've given it like a brief moment to touch the water, and it just splashed, and now a little bit of the box is submerged. What's changed? Well, one thing that hasn't changed is the force of gravity. Gravity doesn't really care if you're in the pool or out of the pool. As long as you're in the same general region of distance from the Earth's center, your force of gravity on your body is not going to significantly change. It will only change if you go way out into outer space or very close to the Earth's core. So jumping up and down or moving up a ladder or up and down the floors of your house never will influence your gravitational force significantly. So we can assume, therefore, that gravity is still going to be pulling on that box with a force of 200 newtons. But something else has changed. The box is now slightly underwater. So it's displacing some water. Water's being pushed out of the way, and as a result, it's going to resist the box. It's going to be pushing off against it. That's the buoyant force that we were talking about earlier. And it's the result of more pressure being on the bottom of the box than there is on the top of the box. Now this is where I'm going to bring up a really important concept that relates to fluids in physics, and that's Archimedes' principle. Archimedes' principle says that the buoyant force that's exerted on an object will always be equal to the weight of the fluid that has been displaced. So what we'll do throughout this example is we'll look at how much water the box has pushed out of the way, and we'll understand that that amount of water that's been displaced will tell us something about the strength of the buoyant force pushing up on the object. So let's go forward in time, but first, what is going to happen to this box? Well, there's 100 newtons of buoyant force pushing up, 200 newtons of gravity pulling down, and the result is there's going to be a net force directed downwards of 100 newtons. So the box will accelerate towards the water again. So it seems like we haven't really caught this box in the moment where it has settled. So let's go forward in time and see if that happens. So sploosh, the box continues to fall down towards the Earth's center. So has gravity changed? Well, no. We already talked about how it doesn't matter where you are in relation to the pool that you're nearby. Gravity's always going to pull on you with the same amount of strength. So gravity's still going to pull on this box with 200 newtons of force, and the water level has risen because the box has been submerged a little bit more. It's displacing more water than it did in the previous example. So Archimedes' principle says that the buoyant force that the box feels will be equal to the weight of the fluid that it displaces. More fluid is being displaced, so there's going to be more buoyant force. So I'm just throwing out a number here and saying 200 newtons might be the buoyant force now. That's double what it was before, because we're displacing twice the water. So if there's 200 newtons of buoyant force pushing up, and 200 newtons of gravity pulling down, what's going to happen to the box? Well, it's not going to accelerate because there's no net force. The forces are balanced in this case, so they cancel each other out. So the box, you could say, is in equilibrium, where it's no longer going to be changing what it's doing. This, in reality, is when the box would be floating, where it would just sit nicely, and we wouldn't have to touch it or do anything to it for it to stay exactly where it is. So this is flotation, when an object is in equilibrium and its forces are canceled out and balanced. So in order to continue this example, we have to imagine that someone reaches out their hand, grabs the box, and yanks it down, just so that we can continue to see different examples of what would happen to this box as it is more submerged. So a hand reaches out, grabs the box, pulls it underwater just a little bit more, and let's look at how the forces look now. Gravity's still going to be the same, still 200 newtons, but what about the buoyant force? Well, again, the buoyant force is equal to the weight of the fluid displaced. We're displacing even more fluid than we were before, because more of the box is taking up that space under the water. And as a result, we're going to feel a stronger buoyant force. There's now an even greater pressure difference between the top and bottom of the box. So stronger buoyancy is the result. So now what would happen when these two forces fight? Well, now there's a stronger push in the upward direction than there is in the downward direction. So now the box will accelerate upwards. So remember, this whole part of the example here was someone grabbed the box and yanked it under the water. Well, now we can say for sure that if they released it, it would go whoosh, it would go up and then start floating on the surface again. Let's take this forward in time a little bit more. Let's completely submerge the object and see what would happen then. Is gravity going to be different in this case? It's not. It's still going to be 200 newtons. We haven't changed any properties of this box, so its weight stays the same. But what about the buoyant force? Well, we're submerged completely, and we're displacing even more water than we did before. So the buoyant force is again going to increase to maybe 400 newtons. So we're finally at this point here where we can't have any more volume of water pushed out of the pool anymore. Even if we take it to the next level and pull it down even farther, which is what I'll do in the next example, we'll see some things are going to stay constant. So this box will accelerate, as it did in the last couple examples, because there's 200 newtons down and 400 newtons up, so this thing is going to shoot up really fast. And now that final example that I mentioned, let's take the box and pull it completely down into the water, even deeper than it was before. You'll notice that the water level in this last example didn't change from the previous one. And that's because we had already taken up all of the volume of that block in the pool. We already pushed that amount of volume of water out of the way. We're not adding any more water displaced here. So if we look at Archimedes' principle, it says the buoyant force is equal to the weight of the fluid displaced. Well, we haven't displaced any extra fluid, so we're not going to get any extra buoyant force. So here's what the forces would look like. Down at the bottom of the pool, the block still weighs 200 newtons, and the buoyant force is still going to be 400 newtons like it was in the previous example, because again, we didn't add any extra pushing away of water in this case. So this box will accelerate in exactly the same way that the previous one did, because it has the same net force, which if you did the math would be 200 newtons directed upward. Now again, as a reminder of where this buoyant force even comes from, I'll throw a couple arrows here to represent the pressure that the water is putting onto the different surfaces of this cube. And you can see that the pressure is greater down below than it is up above. But some of these pressure forces are actually going to cancel out. Can you guess which ones are going to cancel out if you look at it for a second? It's the ones on the left and the right. Those cancel out because they're equal on both sides of the box. But the ones on the top and the bottom, those are not equal because they're at different heights in the fluid. And as we discussed, the deeper you are in a fluid, the greater your depth, the greater pressure you're going to feel. So it's the top and bottom of the box that are kind of warring against each other that results in that 400 newtons of buoyant force right there. Now this is the case for cubes, but it's also the case for spheres and cones and irregular shaped objects. It's just simplest to represent this with a cube. It's easiest to see this way, but this works the same for all objects. So now that we know what buoyant force is and what makes it stronger or weaker and how it can influence the motion of an object, let's now compare two different objects with different densities and see how they behave in a fluid together. In this case, we're going to compare the box from the previous example, which had a weight of 200 newtons, to a beach ball, which is filled with air and as a result is much less massive and so it has much less weight. So I'm going to change it by a factor of 10 and say that the force of gravity on that beach ball is 20 newtons instead of the 200 from the box. Let's assume that these objects have the same volume, just for the purposes of not needing to worry about comparing how one is bigger than the other or anything later on. Let's just take that variable out of the equation. What will these two objects do when you release them? Well, gravity's going to pull on both of them and accelerate them both towards the ground, and we'll go forward in time and just give them an opportunity to splash into the water and settle wherever they want to settle. So once the dust is settled, the box and the beach ball are both going to be floating because they're both less dense than water. But you'll notice that the beach ball is floating a little bit more. Or another way to say that is a greater percentage of its volume is above the water surface level, and a greater percentage of the box is below the water surface level when you compare the two. So this is a trend that you'll see continued throughout examples like this, is that when things are less dense, they tend to have less of themselves submerged in water, and when things are more dense, they tend to be more submerged in water. So what kind of forces would be acting on these objects? Well, gravity, as we saw in the last example, does not change depending on your relative position. And so the force of gravity on the box is still going to be 200 newtons directed downward. The force of gravity on the beach ball is still going to be 20 newtons directed downward. But remember that we gave these objects an opportunity to balance out what they were doing, and they're just kind of floating and they're happy. In other words, they're in equilibrium. So if they're just happily floating in equilibrium, and we know that there are gravitational forces pushing them downward, we know that there should be something happening in the upward direction to cancel out gravity. So that's the buoyant force. What we'll see here is that when these two objects float, the place where they are happiest is the position where the buoyant force cancels out gravity. That's when they reach equilibrium, and that's why they stop moving at a certain point, because their forces cancel. So when we think back to Archimedes' principle that we saw in the previous slide, it says that the buoyant force is based on the weight of the fluid you displace. So for the box, it's displacing a little more fluid, so it has a stronger buoyancy force. And for the balloon, it's not displacing a lot of water at all, just a little bit, so it has just a little teeny tiny buoyant force. So you can see the relationship there. Now, what if we took these two objects and we pulled them under the water? Remember that they have the same volume, that's what we're assuming, so that's not going to be a factor. They both are pushing water out of the way. Gravity's going to pull on both of them the same way it did before, so that's not going to change. 200 newtons for the box, 20 newtons for the balloon. But assuming that those objects have the same volume, they're going to have the same buoyant force as each other, because unlike the previous example, where one of them was pushing more water out of the way than the other one, so they had different buoyant forces, in this case, these two identical volume objects are going to be pushing identical volumes of water out of the way. They're going to be displacing the same amount of water. Therefore, they will both feel the full buoyancy force, which on the previous slide we said was 400 newtons, so I'm just going to keep that abstract number here. So if we know that both of these have an upward force of 400 newtons because they're fully submerged, and if we know that their gravity forces are less than the 400 newtons, we know that there's going to be a net force directed upwards, so the objects will both accelerate upwards. So let's take this example of comparing two different objects with different densities, and let's change it up a little bit. Now I'm going to ask, how will a less dense than water object compare to a more dense than water object? I want you folks to be able to see a lot of different examples of what objects tend to do when they're in a fluid, and so I'm throwing all kinds of different possibilities at you here. So again, assuming that these two objects have the same volume, the box from our first example and a rock with identical volume but different mass, let's release those two. So gravity is going to pull on these two very differently because the rock is going to be much denser. I'm going to say it has 800 newtons of gravitational force pulling it down. When those two objects fall, and they will fall because they're going to accelerate downward because there's no other forces acting on them, they'll splash into the water. So I'm going to go forward in time a little bit. So there they are. The rock is more dense than water, so it's obviously going to sink. The block is less dense than water, so it's going to float. Let's look at the forces acting on these objects. Gravity is not going to change. Gravity always remains the same when you move, up and down a couple feet or meters or what have you. So that will never ever change in our physics examples. So force of gravity on the box, still 200 newtons. Force of gravity on the rock, still 800 newtons. What about buoyant force? Well, the block is only about half submerged in the water, and we saw in the last example that equated to about 200 newtons of buoyant force. But the rock is completely submerged under the water because it was dense enough to sink. So the complete submergence means that it's going to have a total of 400 newtons of buoyant force, if we're sticking with the numbers that I've been using throughout, which again are just abstractly chosen. So what is the box going to do? Well, its forces are balanced out, so it's going to be in equilibrium. It will not accelerate in any particular direction. It'll be happy and it'll just float there. What about the rock? Well, the rock has 800 newtons directed down and only 400 directed up, so it's going to continue to accelerate towards the bottom of the swimming pool or the cup or whatever container we have here. So it looks like there's still some action left to be had here. So we'll go forward in time, and I'm really going to change things up here. I'm going to say two different things are happening to these objects. Someone is taking out their hand and they're grabbing the box and yanking it under the water, and the rock, we're just letting it fall. I'm just, again, throwing a couple different scenarios at you here. What's the forces going to look like here? Again, gravity never changes in these circumstances. Force of gravity on the box is going to be 200 newtons. Force of gravity on the rock, still 800 newtons. And the rock has now hit the bottom and is no longer moving. So what's the buoyant force on these objects? The full buoyancy force of an object of this volume, we already determined, and we're saying they have the same volume, is 400 newtons. So that's what they're both going to be feeling because they're both fully submerged. But what happens to the two of them? Well, the box now has a net force upward because the up force is stronger than the down force. So if you were to release the box from your hands, it would go whoosh and go back up to floating and be happy again. But what about the rock? Well, the rock, and you've done this before when you were a kid, or anytime you go into a lake or whatever and you toss a rock, it sinks to the bottom and hits the ground and stays there. So the rock is in equilibrium. But how can it be in equilibrium? We know it is because it's staying still. It's not accelerating anymore. It's just staying on the bottom. But the forces don't seem to be balanced. We can't get any extra buoyancy force from going deeper. It's still the same difference of pressure from the top of the rock to the bottom of the rock. So there's something missing here. The 800 isn't being canceled out by the 400. So can you figure out what kind of force is here that's canceling out the extra 400? Well, it's actually the normal force. You may recall that normal force is a force that a physical surface provides to an object when it's supporting its weight. Right now I'm sitting in a chair, and the chair is putting a normal force onto me to support me and prevent me from falling towards the ground. So, the normal force and the buoyancy force are both adding together to cancel out the gravitational force, and that's why the rock is in equilibrium. So now you can see how buoyancy force, gravity, and even other types of forces like tension or normal force, how they can all play a role in physics problems that involve fluids. There can be up to 4 or even 5 forces on some of these objects that you'll see in the problems that you're doing. So now that we've seen all these different examples and possibilities, I'm going to give you a conceptual problem here, and I want to see what you can do with it. Here's the scenario. The objects to the right are lowered at a constant velocity by a steel bar, so that they can be submerged into the fluid below. At what point will the buoyant force be increasing the fastest for each shape? Will it be when the shape first touches the fluid? Will it be when the shape is halfway submerged? Or will it be when the shape becomes fully submerged? I'll give you a couple seconds to think about this. And remember, I'm not asking when will there be the greatest buoyancy force. I'm asking, when will the buoyancy force be increasing the fastest? Give you 10 seconds for this. Think you have an answer? Let's advance this situation forward in time to see what it would look like when the shapes are halfway submerged. That might help. The yellow triangle is going to enter the water first with just its tip, and that tip represents a very small area. So at the second that it enters the water, the fluid, it's not going to be pushing a lot of water out of the way. So why is that important? Why does that relate to buoyant force? Well, remember, Archimedes' principle tells us that the buoyant force that an object will feel is equal to the weight of the fluid that the object displaces. So if the tip of the triangle isn't pushing a lot of water out of the way, then it's not going to be generating a large buoyant force. So it's not going to be increasing very much at the beginning. But it will be at the end. In fact, that's the answer to the first part of this question. The yellow triangle will be increasing its buoyant force most rapidly at the end, when it's, almost completely submerged. And that's because the top of the object is very large in volume, or area, depending on if this is 2D or 3D. And so that larger area is going to push more water out of the way. What about the pink? Well, the circle is widest in the center. So that means at the point we're actually looking at it right now, that's when the largest amount of water is being pushed out of the way each second. So that's when the buoyant force is going to be added on the fastest for that shape. Is going to be in the middle of the process, which is actually the snapshot that we're looking at right now. And then finally, the last one, the flipped upside down triangle, the orange shape, that one, the moment it enters the water, is going to be immediately gaining lots of buoyancy force because it's pushing in its largest area, its largest section of itself right from the get-go. So that one's going to feel the greatest increase in buoyant force at the very beginning of its journey. So I hope this presentation has helped you to understand what buoyancy force is, what makes it stronger or weaker, and how it can influence the motion of objects. I'll see you in the next video.